I'm density. You see me in such fine quality, epic chemistry educational videos such as Densities for the Thick-Headed, Part 2, and Mass, Volume, and Density, What's the Connection, Part 4. Okay, this is a review for Honors Chemistry for the Chapter 3 test, naturally. Oh look, my sign fell off. What do you know? Guess what? I'm putting it back up. Okay, so here we go. I figure if the pop stars can do this with all their little Illuminati signs, why can't I do it on my videos? Yeah. Okay, so let's look at it. What are we looking at tomorrow's test? Okay, well, there's a number of things. We've been talking about measurements. We've been talking about the metric system. We've been talking about converting from one measurement to another, or using bridge notation. We talked about integrity. We've talked about accuracy and precision. We've also talked about significant digits. So this is like a lot of stuff. Where do I even go? Well, I actually happen to have the test right here, and I'm just going to look at it, and the idea is I'm going to show you guys, hey, what would be kind of important for you to know for the test tomorrow. So let's look at this. I would be definitely looking at density. When I look at density, that's equal to mass over volume. Now, there's a couple of units for density. We've got grams per cubic centimeter, or grams per milliliter. Now, those, they mean the same thing. You'd say, but wait a minute, what's the difference between cubic centimeter and milliliter? Well, 1 cubic centimeter is equal to 1 milliliter, okay? Cubic centimeter, we apply that to solids, like this handy-dandy smartboard pencil. Whereas grams per milliliter, that's what's inside this little contraption. I like my water cold. Just how I give pop quizzes. All right. So look at density here, mass over volume. So you could get a problem like your friend found a block of unknown material, and you measure the block to be 1 centimeter, okay, by 1 centimeter by 1 centimeter, and turns out the block weighs 8 grams. Okay, what's our density? Well, density is mass over volume. We have our mass, we need to figure out the volume. Okay, well, it's a cube, right? So length times width times height, 1 times 1 times 1, or 1 centimeter cubed, because centimeter times centimeter times centimeter gets you your centimeters cubed. So our density is equal to 8 grams per 1 cubic centimeter, or 8 grams per cubic centimeter. That's it. All right, well, what about if you had another situation where they give you the density of something and you're asked to find something else, like I have the density of 12 grams per milliliter, okay? And I found my mass is equal to 6 grams. What's going to be my volume? Okay, well, if density equals mass over volume, that's our basic formula, right? So 12 is equal to 6 over x. Solve for x. Okay, we'll solve for x. So we're going to multiply x on both sides, so that'll be 12x is equal to 6x over x. X over x cancels out. So that means, as we push on, 12x is equal to 6
Therefore, x is equal to 0.5 milliliters. And there's your solution. Okay. I do need to move on, ladies and gentlemen. I do need to move on. Okay. Now, let's look at the metric system here for a moment. What would be useful to know about the metric system? Well, you probably would want to know about the SI. The SI is System International, which is the same as the metric system. Okay? The SI System International, which is the metric system. Now, that being said, we have to look at some prefixes and some basic units, things like that. Well, prefixes. What are the prefixes you would need to know? Well, kilo, milli, centi. Those would be the three prefixes I would hold you accountable to. So kilo is 1,000 of anything, and I'm not giving this on the test tomorrow. 1/1000 is milli, which is equal to 0.001. Okay. Centi is 1/100, which is equal to 0.01. So this is what we have. Those are the prefixes that I would expect you guys to know. All right. What's up with basic units? Okay. Basic units, or base units. You have one for length. You have one for volume. You have one for mass. So those are the three, and one for time. Okay? Those are your basic units. Now you say, how can I tell if it's a basic unit? Well, let's look. For example, we have the kilogram. We also have the milligram. And we also have the centigram. Okay, so we look at the kilogram, the milligram, the centigram. What in the world? How do I know what's the basic unit in there? These three things all talk about weight. But if you look at the names themselves, there's a name that sticks out as all three have them, and that's your basic unit. The gram is the basic unit for weight. So, what if we substituted, instead of weight, now we're going to look at distance, length, if you will. What is that going to look like? Well, you have, let's say, kilometer, millimeter, centimeter. What would be the basic unit for that? Why, that would be the meter. So the meter is also a basic unit. Okay? So you got the gram as your basic unit for the weight, the meter for your distance. How about volume? Ooh, milliliter, centiliter, kiloliter. Ooh, hey, liter, what do you know? That's also another one in there. Now what about time? Time. Wow, yeah. Time's a little bit different. And I'm just going to go flat out and say that, you know, there are milliseconds out there when we talk about how fast somebody is going. And that, ladies and gentlemen, would in fact be the second, would be your basic unit of time. That's there. All right. All right, now conversions. You should be able to make conversions. If I'm going from 7 centimeters equals how many meters? Should be able to do that. That's where the bridge notation comes in. So I want 7 centimeters, and I want to end up with however many meters I got. What do I know? I know that in 1 meter, I have 100 centimeters. I am not going to give you that information tomorrow. You need to memorize how many centimeters there are in a meter, how many millimeters there are in a meter, how many kilometers there are in a meter, okay? Those are things I would expect you to know. So, this is the bridge notation. We did that changing seconds into days, how many seconds there were in a century, and all that. So, in this case here, I find that the centimeters will cancel each other out because when we multiply it across, centimeter over centimeter is going to be 1. Okay, so here's our meter. So I've got 7 over 100, which if I divide it out, it's going to be 0.07 meters. And that would be our answer for that. So that's an example of conversion. You should be able to do that. Okay? And let's see, what other things do we need to talk about? Okay. Yeah. Other things to talk about. Let's talk a little bit about precision and accuracy. Okay? If I were to look at the idea about precision and accuracy, I have to look at bullseyes. In our wonderful, perfect world, if we had something where the precision, the measurements were very close to each other, that's the idea behind precision, and accuracy, how close you are to the actual value. Okay, precision and accurate are good things when we hit it on the head. And that would be precise and accurate if we go and we make our measurements and hit it very close. And they're pretty accurate at the bullseye. Think of it that way. But I could also make precise measurements and not be accurate at all. This is precise, not accurate. That's a bummer. Now, I could be accurate but not precise. That's a little bit... This is accurate but not precise. Okay? And if I look here, this is neither accurate nor precise. Okay? That would be kind of important. But what about when we talk about precision in measurements? How do we go into that? Well, if you have equipment that measures 1.000 grams, you have another piece of equipment that says 1.0 grams, and you have another that says 1.00 grams. These are devices, they all do the same thing, they measure, they weigh something. Now the question comes down to is, which one has more precision in their measurements? The more decimal places you have, the more precise your instrument is. See, that's a pretty important idea. The less decimal places that you have, the less precise that your measurement is going to be. And thus, this would be the most precise. Okay? We didn't stress accuracy. We're just looking at precision here. Okay? Any questions? I thought not, because you're watching a video. Okay, let's see. Let's get into integrity. Ooh. Oops, wrong thing. Let's get to integrity. What is that all about? Well, if you look at the idea about integrity, we talked about when scientists are reporting things, when they're making measurements, they're doing their calculations with the measurements. That's when we get into integrity. Now, integrity, it's based off of being honest with your measurements. We're not saying precise or accurate, but the idea is that if your measuring instrument only goes to 2 decimal places and your other measuring Your other measuring device goes to 4 decimal places. The one that you're going to have to do your reporting when you do your calculations is to 2 decimal places. Why? Because that is what's limiting you. If you report it to 4 decimal places, you're basically lying because this is limiting you. On the other hand, if you just simply report it as 1 and that's it, then they're going to say your work is sloppy. You're not doing a good job. Okay. Let's move on because I need to wrap up here. I need to wrap up and talk about significant digits. This is the one that's probably got a lot of people confused on that, and I can understand. So if we talk about 1, 2, 3, 4, 5, 6, 7, 8, 9, those are significant digits, okay, typically. 0, it can be, it cannot be, it depends. So let's look at this. If I look at 1, 2, 3, 4, 5, how many significant digits do I have? Now, some people would say 5. Other people say, wait a minute, he's trying to trick us here. I'm going to go with 0. And you know what? If you did go with 0, congratulations! You made it. You are it. There's no unit. When you have no unit, they don't count. Now, how many significant digits do I have? Well, I've got 1, 2, 3, 4, 5 significant digits because this 0 doesn't count. It doesn't count because it's not in between 2 real numbers and there's no decimal after it. If I went 1, 2, 3, 4, 5, 0 point grams, then it's 6 significant digits. If I went with 1, 2, 3, 4, 5, 0.01. Now you have got 6, 7, 8 significant digits because these zeros are in between 2 non-zeros. So that's going to get me 8 significant digits. This will get me 6 significant digits. This will get me 5 significant digits. If I do 1, 2, 3, 4, 5, it's 0 significant digits. Okay, let's keep going. If I got 0.001, that makes it 1 significant digit because these zeros aren't counted. If I go 0, 1, 0.001, that is 5 significant digits. Okay, if I go with 1.00100, and we'll assume that there's grams, you have 1, 2, 3, 4, 5, 6 significant digits. Okay, because these 2 zeros are telling you how far it carries out. Okay, and it does get confusing. If you got 0.00100, okay, grams, it's only 3 significant digits. These zeros do not count as significant. Okay? Yeah. All right. Now let's look at multiplication and division. What you're interested in is the number of decimal places. It has to match for your smallest one. So 2.52, 3.533. When you do your answer, it has to be in 2 decimal places. Okay? It has to be in 2 decimal places, whatever, you know, the number y is. It's got to be to 2 decimal places, not 3. Okay? If you're doing adding and subtracting, okay, then you look at the number of significant digits that are there. Doesn't matter how many decimal places you got at that point. Okay? So 1.01, and then you have 2.225. If you were adding those up, okay, you'd have 3.235, right? Well, how many significant digits do we have? 3, that's our